Am I live? How's the mic level? Good? Thanks so much for sticking around till the last afternoon of the conference. It's really good to be here. I was one of the attendees and speakers at the original PyData back at Google in 2012. And it's been really fun to see the conference series grow over this time and also to see the community grow as well. And it's great to be here. So I want to talk to you about a new project that Jake Vanderplas and I have been working on for just under a year now. We just released the 1.0 release of Altair back at SciPy in early July. We're really excited about this project, and I think I'll just dive right in. So want to take a step back first and talk about visualization in Python. And if you've done anything with visualization in Python at this point, you're probably sitting there thinking the following right now: oh no, please, not another visualization library in Python. I already use matplotlib, and when that doesn't work, I have to jump out to Seaborn, and when I want interactivity, I use Plotly or Bokeh or BQplot, and sometimes I get sick of all of it, and I just go over to R and use ggplot2. I don't need something else to keep track of, right? Why, what's behind the current situation? So there's many powerful libraries for visualization in Python. Matplotlib, the ones I've mentioned here. Each of these libraries does certain things very well. And ultimately, just about any visualization is possible in Python. And even there's some bright points in the API design of these libraries and the abstractions. A lot of them are inspired by or modeled on Wilkinson's grammar of graphics. However, there's also a lot of pain. Visualization is a persistent and significant source of user pain. I see this a lot when I'm teaching. We see it a lot in our work with on Project Jupyter. Because Jupyter is the user interface for all of these tools, users tend to complain to us about all of the tools. So they'll be using Jupyter and complain to us about scikit-learn or about matplotlib. Visualization is one of the top things we're hearing from people. This first quote is actually me. I've been using matplotlib for about a decade, and I still have to look most things up. Or you might hear people say, I love Python, but I fire up RStudio to do visualizations and ggplot2. Why is that? There's a sparse handling of statistical visualization. I'll talk more about exactly what I mean by that. Categorical data, date-time data, and users have to write code even for incidental aspects of visualizations. New and experienced users have to track and learn all these different libraries and make decisions about what library to use for a given task. And many of the very basic things are still horribly complicated. Here's a simple example. So sometime when you get home, fire up the Jupyter notebook and import matplotlib. Grab a data frame of your choice. Make a 2D scatter plot of two quantitative columns. You're probably just going to do matplotlib.scatter. Now facet your scatter plot, or trellis your scatter plot by categorical column. You might dig into like Pandas built-in plotting. You might go over to Seaborn and see if it has something along those lines. You may Seaborn has a low-level API for faceting. You might start to look at. Now try faceted histograms. And you may think, well, gosh, Pandas worked great for faceted scatter plots, but oh my gosh, it used to not handle faceted histograms. Maybe they fixed that now. I don't know. I can't keep track of it. And now color the pointer bar by the hour of a date-time column. And you're going to realize, oh gosh, matplotlib's date-time handling isn't that great. Pandas's date-time column rocks, but Seaborn, I'm not sure actually. Now try teaching all this to someone who's learning data science with Python, or try convincing an R user that Python is really awesome and that they should use it. So what do I mean by statistical visualization? There are many different types of visualizations, and statistical visualization is a very small subset of the overall types of visualizations that can be performed. And here's the simple, concise way of thinking about that. First, the data to be visualized is in a data frame. So it's a tabular format, sort of like a spreadsheet. And the data frame is in a tidy format. The tidy format is something that Hadley Wickham sort of introduced the language about. A very short summary of that. The columns are observed variables of a given data type. So quantitative, categorical, date time. And then the rows are samples from some observation. And typically the data is mapped to visual properties using a group by operation. And you'll see more of how this emerges. It's not obvious when you start doing visualization that there's a group by going on underneath, but this is, I think, one of the key properties of statistical visualization. And the reason, or one of the reasons I and others refer to it as statistical visualization is that the groups in the group by operation in this context with a tidy data frame correspond to conditional probability distributions. Visualization grammar. Statistical visualizations can be expressed with a small number of abstractions that form a visualization grammar. My training is physics, and in physics, we really like very simple models that have a small number of abstractions that you can reuse in different ways, right? So for example, a great example is F equals ma. It is Newton's laws. Once you know the force on a mass and you know its mass, you can solve that differential equation and find the acceleration. What's fantastic is it's a very simple model, but it applies to a good fraction of our universe. So it's few abstractions that can be applied across a wide range of situations. A visualization grammar is similar to that. So there's sort of different layers in a visualization grammar. First is the data, and this is really the input data that would be in the tidy format that I referred to. Next is that the data is typically transformed. There's grouping, aggregation, summary statistics, projection, and layout. Typically in Python, we think of transformation as being something that you do before visualization. And I think one of the big revelations that I had is that when you're doing statistical visualization, it's really difficult to do all the transformation before the visualization is done. You really need to build a data transformation pipeline into the visualization process itself. Next is scales. Scales map data values to visual properties. The way I think of scales is that there's sort of three basic data types: quantitative, date time, and categorical. And then there's visual properties: color, shape, facet, row, the position in a row facet or a column facet. And you need a way of mapping from all of those data types to all of those visual properties. So there's maybe n data types and m visual properties. You can think of needing a total of n times m scales that know how to map across those different things to perform all the visualizations that you might want to perform. If you want to think of sort of where are the existing tools in Python weak, this is one area. Tools like matplotlib tend to be really good and have scales that can map from quantitative columns to properties like x and y position and color. But when you get into categoricals and date times, mapping to shapes or other things like that, they're quite weak or have no story whatsoever. Next is guides. So guides are things like axes and legends that enable you to visualize a scale. And then finally, there's going to be marks, some sort of shape or mark that represents the data on the visualization. Declarative APIs. This is something that we've been doing with Project Jupyter for a long time now. Both the notebook format and our message spec that the front end uses to talk to kernels are declarative. And so it's something we've been doing, although we have, honestly, in Jupyter, I think the power of that is sort of beneath the surface a little versus an imperative API. The first specifies what should be done. Imperative specifies how it should be done. Declarative, you have the how is an internal detail that the user never really worries about. All they say is get this done, and I don't care how it gets done. In an imperative approach, you have to provide detailed logics for all of the individual steps along the way. Declarative separates specification from execution, whereas imperative, there's sort of a sensitive dependence on initial conditions with imperative APIs that if the what changes, the steps may change completely. And that's really difficult and painful from the user perspective. So why declarative API? First is usability. The what question is usually closer to the user's end goal than the how question. Honestly, most users, when they're working with data, would love it if it were entirely magic, right? If it would like read your mind and then magically do all the pre-processing and the transformations and the visualizations and the machine learning, like that would be fantastic if it just magically read our minds. And the thing that it would have to read about our mind is the what. What are we trying to do? What questions are we trying to ask? That's usually closer to a declarative approach. Also, I think you'll see here that a declarative API, users have to write less code, and there's fewer abstractions, so there's lower cognitive load, leaving more of your brain power for thinking about the actual important questions. But there's a lot of other side benefits that are really fun. One is that there's a natural serialization format, such as JSON, for sharing and portability. It's also possible to auto-generate APIs, code, examples, and tests. We'll talk more about that. It's much easier to support multiple languages. The visualization tools today that do support multiple languages are typically built on top of a declarative API underneath. And then performance. With an imperative API, it's really easy for the user to make things slow. Well, it's easy for them to make things slow, hard for them to make things fast. They have to be responsible for that. With a declarative approach, the implementer can be responsible for performance. Obviously, that places a larger burden on the implementer, but that's the idea, right? That the user has less burden. So, given this background, how do we map out the current space of visualization tools? So here's a little, I guess it's a pictorial chart with imperative versus declarative, or declarative on the x-axis, and then ease of use and versus powerful. I'm not really happy with these labels, ease of use and powerful being the labels. I'm not quite sure what to call it, though. I think it's probably more of a continuous scale than a categorical, where one is sort of how high level versus low level. It's ease of use is one aspect, powerful is another aspect. In the lower corner is matplotlib. Matplotlib is extremely powerful. You can basically get matplotlib to draw anything you would want, but it's pretty much imperative. One of my favorite tweets about Altair has been someone who saw this and said, actually, this is why I use matplotlib. Right? Notice it's the only tool down in that left corner that's extremely powerful and imperative. Right? Seaborn, much less general, so it's not quite as powerful. Still imperative, but it's easier to use for a lot of things. Right? If Seaborn happens to have a chart that is the chart that you want, it's awesome. It's really nice. Down here, declarative, but powerful. There's tools like D3.js, Vega, Bokeh, Plotly, and BQplot. It may not be completely obvious to you that these are declarative, but for the most part they are, not entirely. And then up in the upper right here, for declarative and sort of high-level, easy-to-use statistical graphics, there's ggplot2, Vega-Lite, and Bokeh charts. Some of these tools, like D3 is a great example, I would say is not purely declarative. There are aspects where you have to provide callback functions that actually implement, sort of take steps along the way. So the Altair is built on top of a JavaScript stack. The lowest layer in this stack is D3.js. Again, it's declarative, mostly declarative. It's a JavaScript library. It's extremely powerful, but also very verbose. So for example, to produce a simple bar chart like this, here's the code that's required for that. And because of that, for a lot of sort of working data scientists, D3 is a bit painful. It tends to be sort of highly optimized for sort of highly customized, sort of bespoke graphics, the type that you see in the New York Times. The next layer up is Vega. Vega is basically a declarative JSON layer on top of D3. What do I mean by that? The Vega JavaScript library takes in a JSON data structure that describes a visualization. An example is shown on the left here. Compiles that down into D3. And so the visualization is still done in D3, but the input for that is not JavaScript code, but is the JSON data structure. It's, again, very powerful, but also still very verbose. It's actually very comparable to the sort of low-level layers of Bokeh and Plotly. Not identical, but a lot of the same abstractions are there. There's also similarities there to BQ-plot. And then on top of that is Vega-Lite. So Vega-Lite, again, is a JSON spec. It's a declarative approach for specifying a visualization. The Vega-Lite JavaScript library compiles that JSON down to Vega, which then gets compiled down to D3 for rendering. So there's sort of a stack of tools here. And you can see here the JSON data required for a simple bar chart is all of a sudden much simpler than it was for Vega. Obviously, each step that you move up this stack, you're losing power. There's fewer things that you can do. The sort of the scope of the visualization tool gets reduced. Vega-Lite is strictly focused on statistical visualization in the sense that I talked about before, whereas Vega and D3 get increasingly more powerful and can handle more arbitrary types of visualizations. Vega-Lite, from a sort of capabilities perspective, is probably closest to ggplot2 in terms of conceptually. What else am I missing here? I think that's good. So I want to talk and introduce you to Altair. So Altair is a Python API for declarative statistical visualizations. It performs no actual rendering of visualizations. You may say, well, that's really weird to have a visualization library that doesn't actually visualize anything. It's just the rendering part, though, that it doesn't perform. What it does is emit type-checked and validated Vega-Lite JSON, which we then hand over to Vega-Lite for compilation into Vega for rendering as D3. So all Altair does is has a Python API that at the end of the day emits this JSON blob that the other JavaScript libraries consume and render. The advantage of this approach is that there's an opportunity for these other visualization libraries in Python, Matplotlib, Bokeh, Plotly, to add their own Vega-Lite renders, right? There's a reason people use Matplotlib, or there's a reason people use Bokeh. For example, if you want absolutely perfect publication-ready PDFs, vector-drawn, Matplotlib is still the tool of choice, right? What we're trying to do is advocate Vega-Lite as sort of a common data exchange format for high-level statistical visualizations. So for example, we're talking with the Matplotlib and the Bokeh and the Plotly developers and trying to convince them to implement Vega-Lite renders so that you could use the API that Altair offers, or just write the Vega-Lite JSON yourself, and then pick which of those renderers you want to use in a given context. Right? If you want the full fancy, interactive, web-based options that something like Plotly or Bokeh offers, you could use those renderers. If you want what Matplotlib has to offer, you could use that for rendering. And in a sense, Vega-Lite then becomes a lingua franca of data visualization. So here's a simple Altair example. Right now, the default renderer that we have works in the Jupyter Notebook. So if you run Altair in the Jupyter Notebook, it just magically works, and it's using the JavaScript libraries for D3, Vega, and Vega-Lite. You can see the declarative nature of this. There's a data set here that's a DataFrame. I pick a mark type using mark circle, and then I encode the data with visual property. So here, the X visual property is going to use the horsepower column. The Y property is going to use the miles per gallon, and then the color is going to be the origin column. And everything is done from there on. So you don't have to say, I want this particular color map, I want a legend drawn with this. And this is one of the advantages, is that with a declarative approach and with a constrained model of visualization, we can make all those choices for you. Now, obviously, you can come along and do some customization. That is possible. But in many cases, when you're doing exploratory visualization, you don't want to mess with that. You just want to see a visualization and say to yourself, no, the correlation that I was expecting is not here. Or, oh, wow, there's a different thing going on here than I thought. So what would this look like in Matplotlib, this same plot? And here I want to show you how a group by operation is sitting underneath Vega-Lite and this type of model. So notice I have a function here, scatter, that makes a single scatter plot for a group, a particular subset of rows in the data set. And then in Pandas, I do group by the origin, which is a categorical column, and then I want to apply that scatter function to each of those groups, right? And so basically, if you want to think of unpacking this as a loop, you would say, for a group in groups, make a scatter plot of that group, picking a particular color that you want to use for that group. Notice though, so you have to do the group by hand in Matplotlib, and you also have to do things like the legend and the axes labels by hand in Matplotlib as well. This is a really simple example. It's not too bad to do this in Matplotlib. Some of the more complex things that Altair and Vega-Lite can do would be quite a nightmare in Matplotlib. So Altair is robust. Why do I say that? Most of the Altair code base is auto-generated from the Vega-Lite JSON specification. So I don't know the exact fraction, but basically our Altair code base consists of a JSON file that just comes from the Vega-Lite repository that specifies what the JSON data structures should look like. We read that JSON file, and then we have a bunch of Jinja templates that we use to auto-generate the Python API that we have. This ensures that we're pretty much guaranteed that as long as that JSON file is an accurate representation of Vega-Lite, that we follow that exactly. This applies to our API, to our entire test suite, and even things like our example notebooks. We are performing type checking and validation of the Vega-Lite that's generated using traitlets. And we're not quite, so we're not mathematicians, so we're not going to make sort of a guarantee of mathematical certainty. But basically, you're more or less guaranteed that the JSON produced by Altair is going to be valid Vega-Lite. It may not produce the visualization you want, but it's not going to cause everything to explode. So Altair is also usable. We have carefully designed this API focused on usability. It's something that Jake and I spent a lot of time with. So for example, all the attributes, it's mostly an attribute-based API. All the attributes on setting are type checked. There's a thin layer of convenience methods. The Vega-Lite spec is rather nested, and from a programmatic perspective, highly nested APIs are difficult. And so we flatten that API slightly using some convenience methods, and we're really happy with how that turned out. And then in a few careful places, we allow things like method chaining, and we've overridden operators such as plus and plus equals for layering. There's intelligent heuristics, such as type inference. Right? You've got a Pandas data frame. Pandas knows what the types of your columns are. In a Vega-Lite specification, you have to specify your data types. We can do that automatically because we have the original data and can do that inference. There's also a shorthand notation for specifying columns, data types, and aggregation. And then there's extensive documentation and over 70 examples. Altair also and Vega-Lite come with a large number of data sets similar to ggplot2, and so we also ship those as well. Altair is powerful. In the Jupyter Notebook, Altair can produce Canvas, SVG, or PNGs. All the visualizations in the Jupyter Notebook will also show up in your notebooks when they're rendered on GitHub or NBViewer. You'll see here in some of the demos, there's a button to just click in the notebook to download as PNG or open the visualization in the online Vega-Lite editor. It's easy to serialize these visualizations as JSON. That's their sort of native format. I don't have an example of this, but you can actually, if you find a Vega-Lite visualization on the internet somewhere as JSON, you can copy that into Jupyter Notebook, and Altair can generate the Python code that would generate that spec, and then you can start to play with it in Python. Again, an advantage of the declarative nature of Vega-Lite. Doing things like that is, I mean, we had to write some code, but it wasn't particularly difficult to do that type of thing. If you want to explore and try out Altair for yourself, there's a conda package for it, there's a pip package. One additional step is needed to enable the JavaScript extension. If you pip install this, conda is able to do that automatically. Altair ships with example notebooks that you can grab just by doing from Altair import star and then calling the tutorial function. And I'm just going to do that now and show you some demos. So I'm just going to import everything from Altair and then call the tutorial function. So what this does is, you can see here on my desktop, it has downloaded an Altair tutorial folder. All of these tutorial notebooks ship inside the Altair Python package. So you don't have to be on the internet to grab that. And then we have just notebooks. And then we display a table of contents of those notebooks here in the actual Jupyter Notebook. Let's see. I'm going to try to get a sense of how much time I have. So I think I want to run through some of the introduction here. So obviously, normally we all don't recommend importing star from anything, but it's nice for simple examples like this. Again, the data in an Altair visualization is a data frame. So here's a very simple data frame. Let's actually put clear. There we go. So here's a simple data frame. And the basic object in Altair is a chart. And you instantiate a chart by passing it the data. And notice, even without anything else beyond that, it can already show a visualization. Now here, it's not doing any visual encoding, so the entire data set is represented as a circle. You can see what the Vega-Lite JSON looks like for that. So you can see the format is really simple. There's a data key that has the data values, and then the mark type is point. Right? Next, you're typically going to want to do the visual encoding. So you're going to call the encode method. Vega-Lite and Altair support the following visual properties. So X, Y, color, opacity, shape, size, row, column, detail, text, label, path, and order. And so let's encode the Y visual property as the A column. And now you can see, so again, go up here. The A column is a categorical. And Altair and Vega-Lite are smart enough to know that a categorical style axes and labeling should be used for that. Again, we can look at the JSON data structure for that. Notice now there's an encoding field, and for each visual property, there's going to be an entry where the field is going to name the column in the data set. The type is going to be the underlying data type. In this case, it's nominal. Vega-Lite and Altair support two categorical types, nominal and ordinal, which represent unordered and ordered categoricals, respectively. There's also, here's the four basic data types. There's a shorthand single letter code for that. So if you need to override the type inference that Altair is doing, you can use this notation, the name of the column, colon, and then a capital letter specifying the type. Let's actually encode both X and Y position, right? So here we have more or less a scatter plot, but again, these are categoricals, and so it's smart enough to handle that. I'm running short on time, so I'm going to skip through some of this. Here are the other marks that Altair and Vega-Lite supports: area, bar, circle, line, point, rule, square, text, and tick. And actually, I'm going to jump over and look at some examples here in the last few minutes. So here's loading one of the data sets that comes with Vega-Lite and Altair. So we can encode the horsepower column as the X position, and then add the Y position as mile per gallon. We can make it a bubble chart by encoding the size as the acceleration. Right? So again, the legend's added automatically. Or maybe we want to encode both color and shape as the origin column, and now we have different shapes and colors used for the different values of the categorical in the origin field. And the thing I want to emphasize, again, is the small number of abstractions. To change the chart dramatically, I'm changing a very small amount in the API. I mean, all I'm changing is the visual encoding, the mapping between data columns and visual properties. Yeah? Yeah, so the question is about interactivity, animations, interactivity. Vega, so remember there's the layering. So there's D3, Vega, and Vega-Lite. D3 and Vega obviously support lots of rich interactions and visual animations. Those are still being added to Vega-Lite. Our expectation is that those are going to show up in Vega-Lite this fall, and then all of that will show up in Altair. Things like selections, cross-filtering, zooming, panning, tooltips, all of that will show up. So let's see here. You can switch to a mark type of a circle rather than a hollow point. Here's a square-based scatter chart, mark square, a text-based scatter chart, right? There's a very consistent, coherent set of scales that know how to map things like text to one of the columns. Or a tick chart, right? So again, all you're doing here is changing the mark type and you get a completely different type of visualization. Yeah?
I'm trying to wrap my head around the declarative style. So, for example, with the marked text, if I added shape to that, what would it do?
Part of what is really interesting about Vega-Lite is that, so you've got a couple different abstractions. One, you've got the columns in your data frame, you've got the mark types, and you've got the visual properties. And it's not always obvious what happens when you combine different combinations of those. The thing that's amazing is that they all work. Like I mean, you can think of there being some three-dimensional cube of categorical date, time, and quantities, visual properties on another axis, and mark types on the other. And you might imagine some of those combinations are going to explode, and they basically all work. Now, they may not produce a visualization that is what you want. The only thing that I can say that we've done is like just start playing around. I can show you an example here from the CARS data set. So here's some faceting. All you do to get faceting is row equals the name of a column, or column equals that. So here's a more complex example. So Y is an origin. X here is an aggregation that's counting. So it's sort of like a histogram, sorted descending. Colors is cylinders, and then we're doing a bar chart, but the stacking is a normalized approach. And so there's a lot going on in something like that. Here's another example of the text mark, right? Basically, you end up with a colored table, right? Where the colors, again, are mapped, in this case, through the means of the miles per gallon column. And so, again, it's not always obvious what you're going to end up with, but you can, with the small number of abstractions, produce a wide range of visualizations. 1 minute. But I want to emphasize that this is a constrained visualization model. It really is. And there's going to be a lot of visualizations that Matplotlib can do, that Seaborn can do, that are outside of the scope of this. And it's important to keep that in mind. Other things that it has is for date-time columns, you often have to make decisions about what time unit to use in your visualization, right? So here, there's a year column. Internally, that would get converted to some date-time column. And I mean, for example, if you start plotting in Matplotlib, you might get seconds, right? Or something silly like that. And so here, Altair and Vega-Lite allow you to specify a time unit. So you can specify day of week, day of month, month of year, day of year, all those different things. Yes?
One more question. How easy is it to change the label of the year to something on x-axis, not
this. Yeah, you can customize all.
I mean, the axis, I'm sorry, axis, 90 degrees split there to actually have.
The angles? Yeah, you can change that. Yeah, there's so notice there's a configure cell here. There's a bunch of configure methods and a rich configuration system for sort of customizing the visualization. So I think I'm going to stop there. There may be
we can have
another
a
question.
little bit of Q&A.
Oh.
So my question was about the time series. Do you guys support resampling or aggregation to different things? So for example, if I have time series data and I want to look at my daily or my yearly or my quarterly or whatever, is that part of a config, or is that a pre-processing that has to be done before?
Yeah.
Instead of just pulling out a piece of the date time?
Yeah, so if you're going from higher resolution time series to lower resolution, it can do some of that. In terms of, Pandas is fantastic for this. You have a lot of control over how you downsample in terms of taking means or averages or first. I don't think that's there right now. So some of the more sophisticated downsampling type of things you would probably want to do in Pandas beforehand.
Could you just explain that, the colon Q syntax? It looks like is that a query or something?
Yeah, so the text before the colon is just the name of the column in your data frame. The single letter after the colon is the data type. And there's 4 data types that we support. Q for quantitative, so just a number. T for temporal, so date time. And then O and N for ordinal and nominal, which are ordered and unordered categoricals. Now, you can oftentimes leave that colon data type out, and we'll infer it. You typically, the most common place you have to add it is if, for example, your date times are strings, not a date time. Or if we get it wrong that it's an ordinal versus a nominal, things like that. Sometimes you do have to override it. Quantities, quantitative columns, I'm pretty sure we always get that right. In this case, I'm just including it sort of to be verbose and show how that works. Yeah? Yes and no. So there's a toHTML method that will export a static web page that has the visualization. And so you could use it on any web page. It does not work like if you want to use this in a terminal-based Python shell or something like that. What you would do in that case is just save the JSON that we produce to a file, and then you'd need to install Node and NPM, and the Vega-Lite package has a command line tool that will auto-generate SVGs or PNGs from that JSON. So you can do it. It's not all built into Altair. It's sort of other parts of the tool chain that can do that. One last question.
So what's next for Altair? Is it depends on Vega-Lite, or is there something else you want to build onto Altair?
Yeah, so the next big set of changes are going to come when the interactive layer lands in Vega-Lite, and we'll need to update the APIs in Altair, the examples, and I think we're going to spend a lot of time sort of understanding how to spell out that interactivity in a declarative manner, but also in a Pythonic manner. I'm not sure what that's going to look like. The other is that and it's sort of on my ending slide, we have all the infrastructure to auto-generate APIs that produce Vega-Lite JSON. It would not be difficult to auto-generate an R API, a Scala API, and all the examples and tests, and it's not, we're not probably going to be the ones that do those other languages, but we have all the code needed for that. I do want to mention, so D3, Vega, and Vega-Lite come out of the Interactive Data Lab, which is Jeff Heer's group at the University of Washington, and in particular Dominique and Arvind are the sort of core devs on Vega and Vega-Lite. So many thanks to them. They've been fantastic collaborators on this.
Okay, let's thank our speaker again.